Welcome. In this video, I'm going to be working Algebra 2 Homework 10.3, which is going to be more practice on rational functions. But I guess this time I'm talking about maybe holes in the graph. So each of these functions has at least one hole in its graph, and we're going to find the coordinates of each hole in these graphs. So what it's going to involve is going to be like factoring the numerator and the denominator and canceling off anything that's common to both. And, pardon me, you know, whatever x value would cause the canceled terms to equal 0, that'll be the x coordinate of our hole, and we'll plug in that x coordinate into whatever's left to get the y coordinate. All right, so factoring the top, I'm seeing that's x squared minus x minus 6. That'll be x minus 3 times x plus 2, because I'm looking for two numbers that multiply to negative 6 while adding to negative 1. So x minus 3 times x plus 2. And then in the denominator, I could factor out this 3, and then I'd have 3x squared plus x, or no, just 3 times x squared plus x minus 2. X squared plus x minus 2 factors into x plus 2x minus 1. But I'd already factored a 3 out of there, so I'm seeing, okay, x plus 2 on both. Okay? So this is equal to x minus 3 over 3x minus 3 with a hole at x equals negative 2. Okay, so I've got the x coordinate of the hole, and then I can get the y coordinate by plugging in negative 2 into the canceled version. Okay, so I'm going to say negative 2 minus 3 is negative 5. Divided by 3 times negative 2 is negative 6 minus 3 more would be negative 9. So y equals 5/9. Okay, that's A. All right, B. G of x is x to the 3 minus 2x squared. I'm going to factor out x squared because there's a greatest common factor. That'll be x squared times x minus 2. And then I'll factor out the greatest common factor from the denominator, and I'll have x times 2x squared minus x minus 6. Okay. Now I'm going to need to do a little bit more work here to figure out what's going to be, you know, how this is going to break up. But I can factor off, or I can cancel off one of these x's. But maybe I'll do that once I've got this thing factored. So I might, switch the color and say, all right, I'm looking for two numbers that multiply to 2 times negative 6 is negative 12. So these two numbers product is negative 12. And then if we add them together, I need to get negative 1. So I'm seeing 4 and 3, and I'm thinking negative 4, positive 3. So I'm going to say the thing in parentheses here is 2x squared minus 4x plus 3x minus 6. And then I'm going to do group and factor. I'm going to say this is 2x times x minus 2 plus 3 times x minus 2. Then I'll factor out the x minus 2's. I'll be left with a 2x plus 3. Okay. So I've got that thing factored up, and I've got that x minus 2 that's going to be common to both. So I'm going to write x squared as x times x for the sake of canceling. And then in the denominator, I had an x, and then the thing I've factored here in pink came back 2x plus 3 times x minus 2. Okay, so I'm going to cancel those off, and I'm going to cancel these off. So this is going to be equal to x over 2x plus 3 with holes at x equals 0 from where I canceled off this x over x. If I plug in x equals 0 into the simplified version, I get 0 over 3, and 0 divided by 3 is 0. So x equals 0, y equals 0. And then also where I canceled off x minus 2, that would be x equals 2. And I plug 2 into the simplified version to see what y coordinate is going to be. That's going to be 2 over 4 plus 3, 2/7. All right. Let's check back in. C is going to be x plus 5 over x squared plus 10x plus 25. So I'm going to say, all right, I've got x plus 5 here, x squared plus 10x plus 25. Okay, I can factor the denominator. I can look for two numbers that multiply to 25 while adding to 10. That's going to be 5 and 5. So I've got x divided by x plus 5 times x plus 5. I can cancel these off. And if I cancel these off, I'm going to be left with a 1 right here, right? Because x plus 5 is just x plus 5 all multiplied by 1. And then this is going to be equal to 1 over x plus 5 with a whole, okay, I'm glad I did this, with what we would think is going to be a hole at x equals negative 5. But if I plug that negative 5 into the simplified version, I've still got a 0 in the denominator. Okay, so there isn't actually a hole. This is a vertical asymptote on the graph of this function, okay, because there's still that factor down there. Okay, so it's not really a hole. And that's not something that's ever going to happen to you on a quiz or a test in my class, but it's something I did need to point out could happen. Kind of like the previous one had the leftover factor in the numerator. That caused the y-coordinate of the whole to equal 0. But if the extra factor, the repeated factor is in the denominator after canceling, that's just going to end up being a vertical asymptote. All right, so for D, that's x minus e natural log x divided by x minus e. So I'm just going to cancel those off right now on the sheet. And so that's just going to equal natural log x with a hole at x equals e. So if we want to find the y-coordinate, we're going to plug into the plug in the x-coordinate of the hole. So y is going to equal the natural log of e, and that's the log with base e of e. And so what I'm asking myself when I'm trying to evaluate this log is what exponent do I put on e to get e? And that would be 1. Okay, so x equals e, y equals 1. E, I think I can fit this into, e is going to be x plus 1, oh man, over x 2 to the x plus 2 to the x. That's a little tricky. Looks like a water spill, but I'm thinking I can factor the denominator here. Yeah, I've got 2 to the x on both of these. So I'm going to factor out that 2 to the x. And this is not a type of factoring we've really done, but if I factor out the 2 to the x, what am I left with here? An x. What would I be left with here? Nothing really. I guess just I would multiply it by 1 to get a 2 to the x. And I can check my factoring by thinking about distributing. And then I've got x plus 1 on top. And so this is equal to 1 over 2 to the x with a hole at x equals 1. Okay. 1 over 2 to the x, that's the same as 1/2 to the x, or 2 to the negative x. It's the type of thing that we've graphed before. But I guess we don't even need to worry about this because we're concerned with the x and y coordinates of the whole. And the y coordinate of the whole, I'll plug in the x coordinate, and I get 1 over 2 to the first, y is 1/2. Okay, there we go. I think I've got one more where we're supposed to find the coordinate of the whole, but yeah, here it is. Okay, it's already factored for us. That's great. X plus 4, x minus 2 divided by x minus 2, x plus 1. Okay, so I can cancel off the x minus 2's. Be left with an x plus 4 over x plus 1, but I've got a hole at x equals positive 2. The y-coordinate of the whole I'd plug into here. I've got 6 divided by 3 is equal to 2. That's it. Okay, so we found the holes. All right, number 2, we're going to actually sketch the graph of each function. And I think there's going to be some of these that have holes in the graph and some of these that are like the first one that are, no, that one has a hole too. These are all hole in the graph type sketches. So just prepare you for that. All right. For A, I'm going to simplify f of x by factoring out the 2 from the numerator. Okay, so this is, once I cancel this stuff off, this is equal to 2 divided by 1 with a hole at x equals negative 1. Okay. So I'm graphing y equals 2. It's been a while since we've graphed something like that, but I go up onto the y-axis with y equals 2, and the equation y equals 2 of the points that have y-coordinate equal to 2, so it's a horizontal line. Okay. I'm just going to decide where I want negative 1 to be, and it's going to be there. I'm going to put a hole there, and otherwise this is just a horizontal line graph. B is looking like something I can probably factor. Okay, yeah, x to the third plus 3x squared minus 4x minus 12. So I'm going to factor the numerator. I'm going to group and factor. Yeah, I can factor out an x squared from the first 2 terms and be left with an x plus 3. And a minus 4 out of the second 2. Divided by x squared minus 4. Oh, whoops. Yeah, I guess I'm going to eventually factor out that x plus 3 and be left with an x squared minus 4, which is something I can cancel. Okay, and I do that, and I just need to be a little bit more careful here because x squared minus 4 has 2 zeros. That would equal 0 if x was equal to 2 or negative 2. So I'm going to say that this is equal to, my graph is going to be y equals x plus 3, something we are very good at graphing, with holes at x equals 2 and negative 2. So maybe I'll graph that. Okay, so I'm going to just draw a line here. That's going to be y equals x plus 3. Whoops, that was supposed to be my hole. And this was supposed to be my other hole. And, oh, whoops. The more I draw on that, the worse it gets. But, okay, that's my y-axis. That's 3. Okay, the y-coordinate of the hole where x is negative 2 is like, is this above or below the x-axis when I'm going to go to sketch it in? If I plug in negative 2 plus 3, that's y equals 1. I know that's above the x-axis, and so I'm going to draw it like that. And that's going to be my sketch of the graph. C is h of x is x minus 3 over x squared minus 3x. So I'm going to factor out the x from the denominator, and I'll be left with an x minus 3. I can cancel these off, and that's, you know, just like 1 over x with a hole at x equals 3. Right. We know how to graph 1 over x. We just learned about that. So I'm going to kind of put in my axes. All right. Y equals 1 over x. I'm just going to decide x equals 3 is right there. And just, oh, whoops, that was supposed to be going down closer to the x-axis, but it's completely fine. Don't worry about it. It's just a sketch. And there's the other part of the graph, but that's going to be the sketch of h of x. Right. Ooh, D. This one looks a little tricky. I don't think we've encountered a situation like this, so I'm going to just copy the problem. F of x is going to equal 1 minus x divided by x to the 3 minus x to the 2. Okay, so I don't know what to do on top. That doesn't really look right, but maybe on bottom I can factor out an x squared. Okay. And okay, what we'll need to know is that, okay, 1 minus x and x minus 1 are almost the exact same thing. They're just off by a factor of negative 1. So I'm going to factor the negative out of the top. Okay, so if I factor a negative out, what do I multiply negative 1 by to get positive 1? That would be negative 1. What do I multiply negative 1 by to get negative x? That would be positive x. And then I've got an x and a minus 1, an x and a minus 1 here, so I can cancel those off. And I've got negative 1 over x squared with a hole at x equals 1. So I've got y equals 1 over x squared, hole at x equals 1. Wait, no, that was negative 1 over x squared. Oh, close call. All right, I showed you what the graph of positive 1 over x squared looks like, so it would stand to reason that negative 1 over x squared would look the same. It's just everything's negative. Okay, so hole at x equals 1. It looks the same except both of the arms go towards the same, go towards infinity or negative infinity. But if I've got a hole here, x equals 1, maybe I'll just graph it that way. It's a little bit more dramatic with, how quickly it decreases down to infinity or, levels off. But we don't need to get into that because we're just sketching. E is going to be g of x equaling x to the 2 minus 3x. It's got a greatest common factor of x divided by, wait, that's x squared minus 3x. I don't even know where I was looking for. Pardon me. Oh, that's the next problem where we're finding vertical and horizontal asymptotes. Anyway, okay. I'm thinking, oh, it's x e to the x divided by x. Oh, that's way easier. Okay. What's the same on both? That's x. So this is like the graph of y equals e to the x with a hole at x equals 0. Okay. We know what y equals e to the x looks like. It's pretty standard exponential growth. But the hole at x equals 0. Okay, so I'm just going to draw an exponential growth curve that has a hole in the graph at x equals 0. What else can you do? All right, and then f is going to be, ooh, man, I was getting pretty creative with these. Let's say, you know, as long as you're good with ones that come back like as a line or a parabola or 1 over x with a hole in it, you should be fine. Bring in all the different types of graphs that we've done this year. But that's good. That's what you need. H of x is equal to x to the 3/2 minus 4x to the 1/2 divided by x minus 4. Okay. I factor out the x to the 1/2. And I'm left with an x, because what would I multiply x to the 1/2 by to get x to the 3/2? A whole x, right? Because 3/2 is 1.5 minus 4. Then I'll divide by x minus 4. And I'll cancel. And so I'm graphing y equals x to the 1/2, which you might recognize better as the square root of x, because we know how to graph that, with a hole at x equals 4. Okay. It's been a while, but we have graphed these square root curves. Okay. Y equals square root x kind of starts at the origin, and it really is a sideways parabola, so it's going to go like that. And whatever we decide x equals 4 is going to be, I'd say something like that. Label it, even give the y coordinate, it's going to be 2, because I'd plug 4 into whatever's left over, and that's going to be my sketch of my graph. And that's all the sketches of those graphs. All right, so we'll move on to number 3. Number 3 says, write the equations of any vertical or horizontal asymptotes to the graph of each function. Okay? And we did these in class where it was linear over linear. This is a bit of an extension, but we're going to approach it the same way. We're going to do long division. And then I'm thinking, you know, same here. Really, if you're good with A and B, that's all I really care about. So 3a, f of x is equal to x minus 3 over 3x plus 2. And for the domain, we're going to grab, or no, I guess not the domain, we want vertical asymptote. Okay. Value that's excluded from the domain, vertical asymptote. That's going to be where 3x plus 2 equals 0, 3x equals negative 2, x is negative 2/3. Then for the horizontal asymptote, okay, if you have just noticed the pattern and it's going to be 1 divided by 3, great. Okay. If you don't, we're going to just do long division. And it's not that bad because it's only ever going to be one step with ones like these. X minus 3 divided by 3x plus 2. Okay, so I say to myself, what do I multiply 3x by to get 1x? That's a third. And then I multiply this through. 1/3 of 3x is an x. And then 1/3 times 2 is positive 2/3. I'm going to subtract that away. Number, 3 minus, or negative 3 minus 2/3, so negative 3 and 2/3. That'd be negative 11/3, I think. And that's my remainder, so that goes over 3x plus 2. Okay. So I see the horizontal asymptote. This thing is getting closer and closer to 0. The bigger x gets, plus 1/3, it's y equals 1/3. If you grow to recognize the pattern where you're just going to divide the leading coefficients, great, good for you. But if you're unsure, that's how we do it. We do polynomial long division. So 3b is going to be g of x equals 4x plus 1 over x plus 10. And I'm going to do the vertical asymptote. Okay, I grab the denominator, set it equal to 0, subtract 10, I get x equals negative 10. For the horizontal asymptote, it's going to be 4 over 1. It's y equals 4. Okay, but if I'm needing to, demonstrate why this is true, I could do long division. Ask myself, what do I multiply x by to get 4x? That would be a 4. Multiply that down. 4x plus 40. I'm going to subtract that, and I'll get negative 39. So 4 minus 39 over x plus 10 is like another way to write g of x. And if I think about the horizontal asymptotes, the thing I'm getting closer and closer to as x goes towards infinity or negative infinity. As x approaches infinity or negative infinity, the denominator is getting really big and the numerator is staying at 39, so it's going to get closer and closer to 0. And I got 4 minus 0, so my horizontal asymptote y equals 4, which is what we said was going to happen in the first place. All right, 3c is going to be... Now, on this one, I do think, just in the interest of time, I'm going to kind of use the shortcut of just dividing the leading coefficients, because that's something you're going to learn about in pre-cal. You'll probably learn why it's true in pre-cal. But the reason it's true is kind of what I've been showing you, the long division. There's just another way that I could show you the same thing. So for h of x, the vertical asymptote, because that's going to take a little bit more work. That's where x squared plus x minus 30 equals 0. I need to solve this quadratic, so I'm going to try to factor. Can I think of two numbers that multiply to negative 30 and add to 1? Yes, 6 and negative 5. So x plus 6 times x minus 5 equals 0. And two things multiply together to equal 0 only if one of them is already 0. So either x plus 6 is 0, or x minus 5 is equal to 0. So I got my equations of my two vertical asymptotes. And then the horizontal asymptote, we're going to take the same approach. We're just going to say, if I divided 2x squared minus 13x plus 15 by this, it would start out, what do I multiply x squared by to get 2x squared? And that's 2. And I would end up with some remainder over something that's going to, grow as x goes towards infinity. And I just have that 2. So that's why the horizontal asymptote is y equals 2. For 3D, I've got f of x equals 3. Yeah, you can see that, 3 over x squared minus 2x minus 35. So for the vertical asymptote, I'm going to set the denominator equal to 0. I'm going to try to factor. Factors of 35, I know 35 times 1 and 7 times 5. So yeah, 7 and 5, that can make negative 2. That would be x minus 7 times x plus 5. Okay, so that would be true when x is either equal to 7 or negative 5. And then the horizontal asymptote, well, this is a fraction, okay? Constant in the numerator, variable in the denominator. One thing this can't equal is 0. Moreover, as x gets really big, this thing is going towards infinity. As x goes towards negative infinity, the denominator is also getting really big, really positive. So, as a result, I'm taking 3 and dividing by more and more and more, and I've got, trending towards 0. And that's really what a horizontal asymptote is. It's somehow telling you what the trending behavior of the function is as x approaches infinity or negative infinity, y equals 0. Okay, for E, I'm going to just copy the problem. G of x equals x to the 2 minus 3x. I'm just going to factor on this. X times x minus 3 divided by x times x plus 5. Okay, so this here, that's going to cause a hole at x equals 0. What I'm left with is something that I can work with and say, all right, well, a vertical asymptote, and x equals 0 is not going to be a vertical asymptote because it's a hole. The hole is still something we would have to exclude from the domain, but it's not necessarily going to be a vertical asymptote. All right, so the vertical asymptote would be where x plus 5 equals 0, that's x equals negative 5. And the horizontal asymptote, and we talked about this in the last lesson, or the last homework, I forgot a P, is this can't equal 1, because x minus 3 and x plus 5 are entirely different numbers. Okay, they're off by 8. And so they're not going to be able to divide and equal 1. Or you could look at it as the ratio of the leading coefficients. 1x divided by 1x is just 1. Okay. You could long divide those if you wanted. It wouldn't be terribly exciting, though. All right. That's E. And then F is, that's a good function. Probably not one that we need to worry about a whole lot in Algebra 2, but 1 over x squared plus 1. Okay, x squared plus 1 is the type of object that is always positive. So if I go to solve for the vertical asymptotes, it'll, I'll be solving x squared plus 1 equals 0, x squared equals negative 1. That's not going to give me a real number. So I'm just going to say none. But the horizontal asymptote, that's going to be y equals 0. because on one hand, we've got a fraction with a numerator that's constantly 1, so that could never equal 0. But also, the bigger x gets in either the positive or the negative direction, the bigger the denominator gets, the smaller the quotient gets, and I'm trending towards y equals 0. Okay. So that was number 3. Hoping it's about to speed up here. Okay, now see the rest of these problems, they don't have as many parts, so I think I'll be able to knock those out a little quicker. All right, this next one, they're giving us one of these linear over linear type functions. We're going to find the domain and range of f. All right, the domain, that hasn't changed with the introduction of holes in the graph. We're going to exclude anything that causes the denominator to equal 0. Add 6, divide by 2, say all x except for 3. For the range, we need to kind of simplify this using long division. So that's what I'm going to do. I'm going to go over here and I'm going to say 4x minus 11 divided by 2x minus 6. What do I multiply 2x by to get 4x? That would be a 2. Multiply that in here. 2x times 2x is 4x. 2 times negative 6 is negative 12. Ah, yes, this was a carefully chosen example. I subtract these away, and if I subtract 4x minus 4x, that's going to be 0. But if I do negative 11 minus negative 12, that will give me positive 1. So this will be 2 plus 1 over 2x minus 6. Okay. And that's just an equivalent way to write f of x. Okay. This fraction here is equal to 2 plus 1 over 2x minus 6 for every x. I guess provided that f of x is defined. Every x except for 3. But, you know, x equals 3, neither of these things are going to be defined, so it's the same. The range, we already have a lot of experience with working with functions like this from the last lesson or the last homework, so that's just going to be y is not equal to 2 for the same reasons it was before. If I'm working y-intercepts on the graph of f, okay, so for the x-intercept, I'm going to set y equal to 0. So that's where 4x minus 11 divided by 2x minus 6 equals 0. You can look at this as like 0 over 1 and cross multiply. Or you could just say, okay, a fraction is only going to equal 0 when its numerator is equal to 0 and its denominator is not 0. So I'm just going to solve numerator equals 0 and verify at the end that I don't get x equals 3 back. So I'm going to add 4 to both sides. Add 11 to both sides, divide by 4, and get x is 11 divided by 4. You know, if I wanted to say that that was 2.75, you could do that. But I think I'm going to just not. For the y-intercept, I'm going to let x equal 0. And so y is equal to 4x minus 11 over 2x minus 6. And I'm going to show you that it would work out the same way if I did this. I probably could have done the same thing solving this for 0. You'd have gotten the same thing. It would even kind of looked the same. But for this one, I'm going to say, okay, y equals 4 times 0, minus 11, divided by 2 times 0 minus 6. So I got a negative 11 over negative 6. That's 11 sixths. Or I could have said, using the simplified version, y equals 2 plus 1 over 2 times 0 minus 6. So that's 2 minus 1 sixth. That's 11 sixths also. So it's kind of how do you want it. And then C is going to be sketch the graph of y equals f of x. So with this one, you know, y equals, and I'm going to want to use this version, like the simplified long divided version, because that'll help me graph most easily. So that'll be 2 plus 1 over 2x minus 6. Okay. So I've got a vertical asymptote x equals 3, horizontal asymptote y equals 2, so I'm going to start my graph there. Vertical asymptote x equals 3. Horizontal asymptote y equals 2. And then, okay, it's kind of a regular 1 over x type graph. I've got a 2 in the denominator, so it's going to be like a half of 1 over x. But, you know, otherwise, it looks like what we would expect. And there we go. Okay, we're happy. Okay, I guess now at this point, I could probably sketch in some x and y axes. Okay, x-axis will be below y equals 2. Y-axis will be to the left of x equals negative 3, probably by an amount that's slightly more than the space I gave. That's not really necessary, but and then that's going to be a good high-quality group sketch for us. All right, number 5. is asking us to consider another function that's linear over linear, and this will be, very much the same. So I think I might just start by doing the long division this time, though. So I'd say 3x plus 2 divided by x plus 1. Okay, what do I multiply x by to get 3x? That would be a 3. So I multiply that over, and I get 3x plus 1. No, 3x plus 3. I'm going to subtract that. Okay, that makes more sense why I would do that. 3x minus 3x is 0. 2 minus 3 is negative 1. So I've got 3 plus negative 1 over x plus 1. We'll know how to graph that too. But maybe if I'm working on finding the vertical and horizontal asymptotes, I'm going to rewrite g in its new form. Okay. So vertical asymptote would be x equals negative 1. It's whatever x value causes the denominator to equal 0. And the horizontal asymptote is going to be y equals 3, because that would be the excluded value from the range. But notice that, on number 4, I asked for domain and range, and on this one, on number 5, I'm asking for vertical and horizontal asymptotes. Really, it's the same question, but at least in this class, but horizontal asymptote, y equals 3. For these functions that end up equivalent to, something like this, it's the same. But I think I've already shown you in this class that a horizontal asymptote can be crossed. So it's not always directly the horizontal asymptote is the value that's not in the domain. In the range, pardon me. Anyway, let's move on. X and y intercepts of g. Okay, for the x-intercept, I'm going to set y equal to 0. Okay. 0 equals 3 plus negative 1 over x plus 1. This is like minus the fraction, right? 3 minus positive 1 over x plus 1, same thing. So I might add that fraction over to the other side. Cross multiply. And then distribute. Subtract 3, divide by 3, negative 2 over 3. Okay. For the y-intercept, I'm going to set x equal to 0, and y will equal 3 plus negative 1 over 0 plus 1. So 3 minus 1 is going to equal 2. And so x equals negative 2/3, y equals 2. C is going to be sketch the graph. So we can do that. Okay, I've got a vertical asymptote, x equals negative 1. Let's sketch that. Horizontal asymptote, y equals 3. Okay, this is a negative 1 over x graph, because that negative 1 over x plus 1. So instead of occupying these two quadrants, it's going to look like that. Just making sure I did it correctly on the other one. And then I'm going to sketch in the axes after that. Okay, y equals 3. Okay, y equals 0 would be the x-axis. Put that there. X equals negative 1. Okay, I need to make sure that, okay, the x-intercept is negative 2/3, so that's still a negative number. So it needs to go to the right of this point here. Right? So that gives me a negative x-intercept and a positive y-intercept, which is what I was expecting anyway. Probably not drawn to scale, but who cares? I definitely don't. Oh, whoops, used up all my scratch paper. So we got one more here. No, one more of these functions that we're going to investigate. Sketch the graph of y equals h of x. All right. Now this thing, y is never going to be able to equal 0 because it's a fraction with a constant numerator that's not equal to 0. So 9 over x squared minus 16. I'm just going to say, and if you got to go to Desmos.com and sketch a graph of this, that's fine. I'm not going to really make you do this on a quiz or a test, but I just thought I'd throw this out here. 9 over x squared minus 16. What's going to happen here? Oh yeah, vertical asymptote would be any x value that causes division by 0. So if x is 4 or if x is negative 4. Okay. Horizontal asymptote is still going to be y equals 0. For the same reasons as usual. Just a fraction can't equal 0. Bigger x gets, the more I'm dividing by, getting closer to 0. So I'm going to sketch this graph. That's going to be -4. This will be +4. And that'll be the x-axis, which is y equals 0. So that's my horizontal asymptote. I guess I can probably, you know, not too risky for me to put the y-axis in right now, because it's just going to be halfway between the two vertical asymptotes. And, all right, at this point, it's like, okay, now what? And now what is, we're going to go ahead and just try some values. We're going to make a table of values, plot some points, and connect some dots. So I'm just going to choose x equals 0. When x equals 0, y, which is 9 over x squared minus 16, well, that's just going to be 9 over -16. And that's a negative number. So I'm just going to plot that down here. I know that this function never equals 0 because the numerator can't equal 0. And I know that it's got to approach these vertical asymptotes. So if it was approaching the vertical asymptote going up, I'd have to cross 0. That's not going to happen. So I know it's going to look like this. Then I'm going to choose something a little bit bigger than 4. I don't know, like 5. Okay, when I choose 5, y is 9 over 25 minus 16. Wait, that's 9 also, so that's going to be +1, which is a positive number. And, you know, maybe I just put that up here. But I know that I've got a horizontal asymptote of y equals 0. I know y can never equal 0 because of what I was saying earlier. It's a fraction with a constant numerator that's not equal to 0. So I know, and it's got to respect that vertical asymptote, so I know the graph's going to look like this. And if I choose -5, the exact same thing's going to happen because I squared -5, and it's the same behavior as +5. So that's 9 over 9, which is also a positive number, and I just kind of draw the same thing over here. And that's how we could kind of like reason our way through making a graph of this thing. But that's probably the last time I'm going to, you know, force you into making one of these graphs. All right. Use the graph of h to help solve the inequality. H of x is greater than or equal to 1. Oh, lucky me. I found where it's equal to 1. And pardon me. It's okay. That's going to be 5 or -5. This is going to be +5. And this is, I'll color y equals 1 in pink. And, you know, this is supposed to be on the same level? Sure. And where is h of x greater than or equal to 1? Through here and back through here. So x being between 4 and 5 and between -5 and -4. So -5 to -4, also 4 to 5, to write this in interval notation. But, okay, I can't include these 4s because the function's undefined at 4. But since it's greater than or equal to 1, it's equal to 1 at 5 and -5. I put squared brackets on those, say it's either of those regions. Okay, but that'll be the only rational inequality we solve this year in this course. That'll be it. All right, now numbers 7 and 8. The graph of ax squared plus 12 over x squared plus b is shown below. Find the values of a and b. This is an AP Calculus question. I shamelessly stole this from AP Classroom for Cal DC. But y'all can solve this. Okay, we can find b easily, right? Because we know it's related to the vertical asymptote. So I'm going to say x squared plus b is equal to 0, right? The denominator is equal to 0 when x is equal to 2. Okay, so I plug in 2, and I get 4 plus b equals 0, and that means b is -4. Okay, A is a little trickier because I haven't, like, you know, been all that explicit with you about the rules for horizontal asymptotes. But we see a horizontal asymptote y equals 3. And I think I've shown you in this video and other times that we can obtain the horizontal asymptote by kind of dividing the leading coefficients of these. So a divided by 1 needs to equal 3. Wait a second, that means a equals 3. That's how we did that problem. But this is a problem that if you're in my calculus class 2 years from now, be confronted with that problem again, because you won't remember. Now the last one, the graph of the quadratic function g of x is shown below. Write an equation for a function that's the same graph as g, but with a hole at x equals -6. All right, well, I think this is going to be, my hypothesis for this original graph would be x minus 2 squared. Because it's like x squared, but its vertex is at x equals 2. But I'm going to just check this by checking another point. Let's plug in x equals 0 and hope I get back y equals 4. Yes, if I plug in 0, I'm going to get back y equals 4. I feel good about that formula. Okay. If I wanted to create a function that had the same graph as g, but with a hole at x equals -6, well, I might just multiply by an x minus -6 over x minus -6 so that I could cancel off and it cause a hole. It's kind of backwards. Why would you do this? But if you needed to make a function with a hole in it, I don't know, because you were preparing an Algebra 2 quiz or something, that's what you would do. You start with what you wanted to have and then add in the extra factor. Okay, that's going to be all for this video, all for this homework. Thanks for watching. Hope it helps.